A century ago, people used the normal model regardless of sample size and assumed it would work. And if the sample size is large enough, it does work pretty well. However, there's problems with smaller samples. And essentially, the sample standard deviation varies from sample to sample, and this extra variation is messes up the standard error, and which in turn messes up the margins of error. The man who first investigated this fact was named William S. Gosset. He realized that not only do we need to allow for the extra variation with larger margins of error, we also need an entirely new sampling distribution model. In fact, we need a whole family of models depending on the sample size. Gosset worked as a quality control engineer for the Guinness Brewery in Dublin, Ireland. His job was to make sure the beer leaving the brewery was high enough quality to meet the demands of the brewery's many discerning customers. And large samples were really not feasible for this, so Gosset would often use samples of 3 or 4. However, the normal model was forcing him to reject what turned out to be about 15% of the good batches. And you just can't have that happen. Something was wrong. And the problem was because of the standard error. With the normal distribution, the standard error for sample means would be this formula you see here, where the standard error is the population standard deviation divided by the square root of the sample size. One problem about this formula is that we usually don't know what the population standard deviation is. But at the same time, we can approximate it using the sample standard deviation, S. So this problem can be solved by estimating the standard error using the sample standard deviation, S over the square root of n. So Gosset figured out that when he used this formula, the shape of the sampling model changed. So it wasn't quite a normal distribution, or the normal distribution wasn't quite accurate enough. So a different distribution was necessary. By the way, this is a formula to keep in mind. Standard error is going to be approximately S over the square root of n, the standard deviation divided by the square root of the sample size. Okay. We've taken a random sample of 100 runners from the 2012 Cherry Blossom 10-mile run in Washington, D.C. We had a rate which was a race of 16,924 participants. The sample data we're going to look at was just a random sample of 100 runners. And you see 4 of the runners right there on the screen. So here's a histogram and summary statistics on the run time of participants, assuming the conditions for the normal distribution have been met. If you notice, the histogram does look more normal. The sample size is at least 30. In fact, the sample size is 100. And it was a random sample. We can assume that the normal distribution has been met, so we can use a normal distribution for this. And let's go ahead and create a 95% confidence interval for the average time it takes runners in the Cherry Blossom Run to complete the race. So here's the information again. The sample mean is 95.61. That's the point estimate. The standard error you get by taking the sample standard deviation. So you take that 15 point... Yeah, clear that. 15.78 divided by the square root of 100, which is 10. But I'll do it the long way. Square root of 100. And you get 1.578, which makes sense. Square root of 100 is 10, so I'm just moving the decimal one place to the left. Oops. So a 95% confidence interval would be the point estimate. So 95.61 plus, since my sample size is large enough and the histogram looks like a normal distribution, I'll use a normal distribution for this, 1.96 times 1.578, and then 95.61 minus 1.96 times the standard error, 1.578. And you can see that I am 95% confident that the average time was between 92.5 and 98.7 minutes. So we are 95% confident that the average runner took between 92.5 and 98.7 minutes to complete the 10-mile race. Now, what if we use a 90% confidence interval for the average run time? Again, I'll assume the conditions have been met. If you notice here that it doesn't look particularly normal, but my sample size is 100. And again, if your sample size is large enough, that's all we need. So the sample mean is 35.05, standard deviation, sample standard deviation 8.97, sample size 100. So the standard error, square root of 8.97 divided by 10, essentially you move the decimal one place to the left, so 0.897. And it would be 90% confidence interval. So 90%, I think the question was 90% confidence. Yeah, all right. Here's the 95% confidence interval. If I want to do 90% confidence, I will take the sample mean, 35.05 plus 1.64 times 0.897, and 35.05 minus 1.64 times 0.897. So we are 95% confident, if you look at the screen, 95% confident that the runners were between 33 and 36.8 years old on average. 90% confidence would be 33.6 to 36.5 years old.